So in today's video, I'm going to talk about numerical differentiation. This is lecture 24 of the optimization series, and I am Dr. Ranjan Ganguly. So we have typically considered that there is some design variable x in an optimization problem, and this leads to certain objective function f of x and constraints h of x and g of x, where x is a vector. Now, in many optimization books and papers, it is presumed that these are functional representations, essentially polynomials or combinations of polynomials, sinusoidal functions, log functions, and so on. But in reality and in actual application, what happens is that you typically have a computer model or computer software which is used to calculate these functions f of x, h of x, and g of x given some input x. And this computer software is often very complicated, very cumbersome, and also takes a lot of computer time. Computer time becomes particularly important because in many situations, if you are dealing with physical simulations, you solve some kind of partial differential equations, and these require discretization of the equations, building up matrix vector systems, and then solving them. And these systems can be enormously large. You're talking of matrices and vectors of the size of thousands or tens of thousands or even millions in some cases, depending on the degrees of freedom of the problem. And therefore, a huge amount of computer time is often taken in this particular software. Now, that is why computer time becomes important. And the second fact is that, in contrast to what you have learned in calculus, where given a function f of x, you can differentiate it. And in fact, it is very easy to differentiate most functions because nowadays you have symbolic tools such as Mathematica or Maple or even in MATLAB. But in reality, if you are getting these functions from a computer code, then you need some method which is numerical to use this code to calculate the derivative. So we only have access to f of x, and we need to estimate the derivative from f of x. So all the gradient-based methods are completely dependent on a good estimate of the gradients for finding a search direction. Now we have even seen that in the case of Newton method and quasi-Newton method, which require calculation of the H matrix or estimates of the H matrix, still the calculation of C vector is required. Now for simple functions, it is possible to differentiate these objective functions and so on. And this is often the case with test functions, which you frequently find in books and also in papers which check out different mathematical methods. But when you turn to the realistic optimization problems, which are there in the wide world at large, you will typically need a computer program for calculating the objective functions and constraint. So we need numerical derivative, and that becomes very important for practical problems. And though this video is primarily focused on optimization, this goes much beyond optimization into fields such as computational fluid dynamics, computational mechanics, and so on. So the first and the simplest possible way to calculate a derivative is to use the forward finite difference formula. And here we take the basic or fundamental definition from calculus, which is that f dash x is limit as h tends to 0, fx plus h minus fx by h. And here we have learned that as h tends to 0, this will become the derivative in the limit. And if you remember calculus, you can try out for different functions such as sin x or x cube, and you can show using limits that you do get the derivative. So that's how the derivatives come. Now we make a jump and we say that f dash x is essentially equal to this, or approximately equal to this depending on the value of h. So going by this formula, if we were to pick a very small h, then this derivative would be a good estimate of the actual derivative. So this is known as the forward difference formula, which is often used in calculations. Now, unfortunately, we will see that this calculation of h is not simple. It is actually quite a non-trivial problem to find an appropriately small h. And that is because there are two types of problems which can take place in this derivative calculation. That is because of truncation and also because of round-off. So we are going to look at both these aspects. So let us look at truncation first. So to find the truncation problems, we expand f of x in a Taylor series as given here. And from the Taylor series, I can immediately write the finite difference approximation of f dash x as fx plus h minus fx by h, and you get this series here. Now you see that f dash x is not really equal to this estimate we have created, but there are certain terms which are essentially also there. So these form what is known as truncation problem in this particular case, and so these are the HOT terms here, and we can write this as epsilon subscript t is half h f double dash plus 1/6 h square f triple dash plus so on. Now the interesting thing to see here that this epsilon t term depends on the higher derivatives of the function, so it will be more in case functions are highly nonlinear and so on, and also that if I bring h to 0, then this epsilon t will be greatly reduced. So that is something we can see here. So actually epsilon t can be driven to 0 if I make h 0. So that's the fact which we have stated here, is that epsilon t tends to 0 as h tends to 0. We also see that epsilon t basically comes from the fact that whenever we take a Taylor series approximation, we have an infinite number of terms and we are truncating the Taylor series here to the first derivative term, and therefore we are losing a lot of information here. And as I mentioned before, epsilon t can be made very small by reducing h. Now, if we were doing this in the mathematical world, there would be no problem. But unfortunately, we are existing in a computer world. And there is a phenomena called round-off because of the finite precision of computer mathematics. And this puts a limit on how much we can reduce h. For example, you can see that when we actually work on a computer, fx plus h minus fx tends to 0 as h tends to 0. For example, if I were to use h as 1 into 10 to the power minus 15 and my computer does not have sufficient precision, then this particular calculation would simply give us 0. And you can imagine doing this on a calculator, and certainly because you have a certain number of digits in your calculator, these things may not come out very well. So this is something which you can intuitively see if you have been familiar with computers, that computers are limited in terms of precision and therefore you cannot lower h beyond a certain point. So if we take a very small value of h, you will of course get less of the epsilon t part, but your round off will be more because you are trying to subtract two quantities which are almost equal, and this is difficult to do in a computer. So let us try to create some value here which we can use, or find some way to essentially calculate h. So let us presume that epsilon p is the precision of the computer mathematics, and then the round off is given by this formula here, which you can approximate by using only the first term, because the second term can be neglected because h is typically small and mod of f dash x is not very large. So therefore, given epsilon p is a very small number because of precision of the computer, the second term we have neglected and the first term is dominant. Therefore, combining the epsilon t and the epsilon r, we get this particular value here, that epsilon is the part due to roundoff plus the part due to truncation. So now you can see there is a clear trade-off here. Reducing h would bring down truncation error, but reducing h beyond a point would increase the roundoff in the computer. So let us try to minimize this particular value. So to find the value of h which minimizes epsilon, we minimize this function here. And again, going back to our basic calculus, we essentially differentiate this with respect to h and set that to 0, which I have done here. And by doing that, I can solve for h as in this equation here. Now, typically, norm of fx and f double dash x are not too large or too small. So this particular value of h is largely going to depend on epsilon p, and therefore there is a rough formula that h could be taken as the square root of epsilon p. For example, if I'm using single precision mathematics, epsilon p is 10 to the power of minus 8, then h would be 10 to the power of minus 4. Now there are many different ways of selecting h. There is no sacrosanct formula. One more practical guideline is to use a perturbation of 1% if the function is not too nonlinear. And I have used perturbations ranging from 1% to 5% depending on functions to create these kind of matrices. Now these are all practical recommendations which you can give for the choice of h, and there is no universal rule for all types of function. So in general, we can say that as h is decreased, the truncation problems will come down, and if it is very low, you start encountering the round-off problems. So you need to find a middle ground between these two extreme situations. Now you can further reduce round-off error by increasing the precision of your computer. So if you are having a double precision computer, which is there in most computers nowadays, epsilon p would be 10 to the power minus 16, and then you even have computers where you can use epsilon p is 10 to the power minus 32 and so on. But again, all those come at the expense of computer time in some cases. So now we look at a more, shall I say, correct formula. And this is by using the central difference formula, which is given here. So central difference formula says that f dash x is fx plus h minus fx minus h by 2h. And we'll derive this in the next few slides. So let us expand the function f of x in the backward and forward directions. So this is the forward direction of the expansion, which we have already seen. And this is the backward direction. So in the backward direction, I have simply replaced the plus h with the minus h. And so wherever the h sign is there, you get a minus. And wherever the square sign is there for h, you don't get any change. So these are the two expressions I get. Now, by subtracting these two expressions, I obtain this equation here. And this equation then lets me calculate something for f dash h, which is fx plus h minus fx minus h by 2h is f dash x plus the error terms. So these are all truncation. So here you can see the truncation terms are proportional to h square and so on. So they are going to be very small if h is small. So the truncation terms are here, and you can calculate the truncation terms and check it out. Now you will have lesser problems in this central difference formula in terms of truncation as compared to the forward difference formula. But again, the problem is that you do need to find one more value of the function, which is at fx minus h. So there are a couple of calculations here in terms of the function f of x. Now, if you want to calculate the gradient vector, you need to calculate partial derivatives, and therefore how you calculate it is that you perturb each component xi by h, and then you subtract it with the function value at x0, so you can get all these particular partial derivative. So each variable has to be perturbed one by one, and the value of the function at that particular point has to be found. And then once you have found all these partial derivative I is 1 to n, you essentially obtain the gradient vector. Now, the calculation of the gradient vector would require n plus 1 function calls, n partial derivatives and 1 for the basic function f of x. Now, why this becomes important is that if your objective function is calculated from some FE code or some computational fluid dynamics code, then the time taken to calculate these gradients may become very large because you often have a large number of design variables. So this is also a case where when you are creating an optimization problem, you need to make sure that your design variables are as less as possible if it is feasible. So of course, in some situations, you may be constrained by the fact that you have to have a large number of design variables, but there are several problems where you may be able to figure out the key design variables by doing some kind of parametric studies or sensitivity studies on the problem. So that is also something very important which can be used to reduce your computed time. So for example, just to illustrate it, let us say we have a software code which takes 5 minutes to calculate a function value, and this is very less in terms of reality where computer codes may take even more time. Now, if you have an optimization problem with 20 design variables, then the gradient calculation would require 105 minutes because this is n plus 1 into the time to run each function, and that is quite a long time, hour and 45 minutes in this case. So if you are doing this many times, because typically the optimization algorithm will call for gradient calculations at every k value, you are going to spend an enormous amount of time on the computer, and this whole problem may take days, if not weeks, unless you have access to supercomputers or something like that. So let us make some general comments on computer time, which we are going to address in some future lectures. So one approach to reduce computer time would be whenever it is possible and you have some kind of functions, you can try to differentiate those functions and solve the problem as part of the computer program. Now, in certain situations, we will see later that we can even differentiate mathematical expressions in terms of matrices and vectors and put them inside the computer program. Now, gradient calculations have to be made many times during optimization, and that is why these become very important. Therefore, in many practical problems, this expensive computer function calculation can become a limitation in terms of the use of various optimization methods. And this is one of the reasons which prevents the percolation of optimization methods to a large number of engineering problems. Though as computers become more and more powerful, and we shall see later in this lecture series that there are methods called surrogate methods and so on, or surrogate models or meta models, where you actually take a computer program and you find an approximation of that program in terms of surrogate models, which are polynomials or Kriging or neural network, and these can dramatically reduce the computer time you require for this problem. So the Hessian matrix is even more expensive, and here as an example I have given the calculation of one particular term of the Hessian matrix, which is a partial derivative. So essentially you have to first take the derivative of the first component, that is dou f by dou x1, and then take the derivative of the second component, and you get this huge expression here. Now each term of this Hessian matrix is going to require 3 function calls, and therefore the Hessian matrix being symmetric, you have to calculate the diagonal and 1/2 of the particular matrix. So you would have n square plus n by 2 terms, and if you include the baseline terms, you would have so many terms here. Now Basically, the important thing to keep in mind in any of these computational algorithms is that the largest term dominates. So again, you see the term which is going to be dominant here is proportional to n square. And therefore, the computational expense will increase with respect to n square. See, unlike in the case of gradient where it was with respect to n. And therefore, as the number of design variables increases, this computer time or function calculation is going to explode as far as the Hessian matrix is concerned. So you can simply imagine if you have 1,000 design variables, n would be 1,000, but n square would be 1 million. So the size of that matrix would be million by million, which is extremely large. So also the Hessian evaluation being very time consuming, practical optimization algorithms rarely use this matrix, but they at least try to find an estimate of this matrix like the B and A matrix we saw in the BFGS and the DFP method. So in most cases, we try to figure out the Hessian matrix using first derivative or gradient information, for example, in the quasi-Newton method. So gradient calculation is of course sacrosanct as far as all the gradient based methods is concerned. And in this chapter, we have seen that typically gradients are calculated using the finite difference method, and most likely you are going to use the forward difference method to calculate the gradients. And if you have the luxury of higher computer time, or if you are having a function which is very nonlinear, then you can think about using the central difference formula. And in both these cases, keep a issue on the value of h. Of course, it is good to reduce h as much as possible because you can then decimate the truncation problems, but you run into the round-off problem. So again, we saw that there are certain ways in which you can reduce the round-off in most computers by using a pretty low value of h, but not an exceedingly low value of h. So again, that ends the lecture here today of lecture 24, and I'll see you in my next video on further methods of differentiation which can be used in optimization as well as in different fields such as computational fluid dynamics and so on.